This presentation focuses on how the graph and the equations in causal networks follow each other. Any change in one has an equivalent change in the other. These slides were organized by Dr. Alemi. A causal network is directed acyclical tree. Each node in the tree is related to its parents and children by arrows. Here we show a simple, directed graph with three types of nodes. All P nodes are parents to X. There is always a directed arc from the parent node to X. Networks also show children. All C nodes are children of X. X is the parent of these children, and there is an arc going from X to the children of X. Causal networks are directed graphs. Every arc has a direction of influence. In this network, the parent node PM influences node X, and node X influences the child node C1. You can walk through a network structure in this fashion. Causal networks are acyclical graph. It is not possible to start at any one point, follow the direction in the graph, and end up at the same place. Let's demonstrate this. If we start at C1, the arc tells us what is next. Then we go to P1. From P1, we end up in X. Then we end up back in C1, creating a cycle. This is not allowed in causal networks. So if there is a cycle, then it's not a causal network. The fact that we work with directed acyclical graph limits the application of causal networks, but simplifies the mathematics of what needs to be taken into account. Here, node C1 is not attached to anyone in the network. It is irrelevant, so it must be dropped from the network structure. Only relevant nodes are shown. In a causal network, there should not be any undirected arcs. The graph shown here is not a causal network because the node P2 and X are associated but have no direction of influence. This is not allowed. In a causal network, the joint probability of all events can be read directly from the structure of the graph. For each node, one identifies the parents of the node from the graph, and the joint probability of the nodes follow from the parents. For example, here we have a possible network that relates patient severity to clinician's choice of treatment and outcomes. In this graph, severity is apparent to patient preferences on resuscitation, treatment choice, and outcome. The parents of treatment node are severity, resuscitation, and provider decision. The parents of outcomes are the treatment received and the severity of illness. Each of these parent-child relationships indicate a dependency in the data. Perhaps more important, the absence of any link indicates independency. For example, the link between provider decision and the health outcome is not present. The model assumes that the provider influences health outcomes primarily through the choice of treatment. Once a treatment is known, the provider's choice is irrelevant. Both the lines drawn in the Bayes net and the lines not drawn informs us of interdependency among the events. Furthermore, these interdependencies allow us to estimate the joint probability distribution. Let us see if we can write the equation for estimating the joint probability of the events in this causal network. In general, we know that only the parents of the node matter. We have abbreviated outcome by O, severity by S, treatment by T, physician decision by M, and patient's preferences for not resuscitation by R. For simplicity, we are assuming that these are all binary events. In other words, there are only two options, either to give treatment or not. there are only two outcomes: patient lives longer or patient dies, and so on. Now we can see what is equivalent statement about this graph in terms of equations. Let us start at the end node, which is the patient outcomes. This is called an end node as it has no children. The equation for this node is given conditional to the probabilities of its parents. Non-parents are not relevant. So here we see that probability of O given S and T is equal to probability of O given S and probability of O given T multiplied by each other. Now we can also calculate the probability of treatment, which is the product of the conditional probabilities of treatment given its parents. Note that the rest of the tree is irrelevant to this calculation. Finally, we need to calculate the probability of severity, do not resuscitate, and physician's choice of treatment. These events have no parents, and their probabilities are merely the marginal probabilities. Now we can put all 5 calculated probabilities together to estimate the joint probability of all events in the tree. The availability of the tree structure and its embedded assumptions of independence has radically simplified what data we need and how we can calculate the joint distribution of the event. Once we have the joint distribution of the events, we can use it to calculate conditional probabilities. This is a relatively simple operation. The conditional probability is the probability of the event divided by probability of all events. So for probability of a particular outcome for a patient that is severely ill, we divide the joint probability of outcomes for severe patients by probability of observing severe patients. The way you can think of conditional probability is that we have selected all patients who are severely ill, and within these patients, we are looking at frequency of observing various outcomes. Note that in this calculation, the joint distribution of two variables, outcomes and severity, is needed, but earlier we had calculated the joint distribution of all 5 variables. To move from the joint distribution of all 5 variables to fewer variables, we have to sum out the missing variables and calculate marginal tables. In this case, treatment, physician decisions, and resuscitation preferences are missing in the joint distribution. Conditional questions are asked often. Bayes-net causal networks provide a useful way to calculate these data. For example, information on comparative value of treatment may be asked. Here we are looking at what are the likely outcomes for severe patients who received a particular treatment. If the joint distribution is known, then the conditional probabilities could be easily calculated. As before, note that in this calculation, the joint distribution of 3 variables, outcome, severity, and treatment, is needed. Bayes calculations provide the joint distribution of all 5 variables. To move from the joint distribution of all 5 variables to fewer variables, we have to sum out the missing variables and calculate marginal tables. Graphs, formulas, and independence assumptions inform each other. Network structure, conditional independence, and joint distribution formulas are based on each other.